Hey, hello everyone. Thanks for attending this talk, and also thank you to the droidCon organization for letting me be here today speaking about Jetpack Compose. It's a pleasure for me, and obviously a great pleasure to be surrounded by so many good speakers. So yeah, let's step into content already. This is gonna be covering the top three libraries we see on that list that compose the Compose library. um, and the idea is that we cover the compiler plugin, the runtime, and the UI, and that kind of triangle of dependencies we got between them to drive the whole Compose experience. But you obviously have other libraries you can see at the bottom, a little bit grayed out, that are like the material and foundation for UI pieces to build our logics, our UI logics, and other additional pieces they provide also, and animation for all the animation APIs and the tooling library for, getting all the tooling we are used to use, also working for Jetpack Compose and the testing utilities and so on. But yeah, we are going to focus on the compiler, the runtime, and the UI elements or dependencies. So let's dive into the compiler already. The compiler is basically a Kotlin compiler plugin that targets the Kotlin IR 1.4 that was released on the version 1.4 of the language. So what it's basically going to do is analyze all your sources to look for composable annotations, and then it will generate convenient IR for each one of those composable functions to add an extra parameter that is going to be the composer to every single one, also on the call sides to those functions. And also add some extra metadata that is going to be used also to feed the runtime and enable and unlock some runtime optimizations, okay? So yeah, the idea is that those functions are somehow going to be converted to or become restartable and cacheable. So that's something that is going to be leveraged by the actual runtime later on. Some ideas of these optimizations we can find can be like a smart recomposition that is possible thanks to how the field is kind of prepared by the compiler plugin, and also because they are restartable functions, so you have the chance of decide what to do with the composition, skip recomposition, even offload composition to different threads or parallelize compositions. That's a potential future optimization that could also happen. The fact that, for example, compositions for different composable elements could be offloaded to different threads or things like that, right? They are also doing things like, for example, inferring what could be a stable API or a stable data, which is some concept, some internal concept they use to kind of know that they are able to apply some further optimizations on top of that by adding some metadata to it and so on. So overall, what the compiler is going to make sure is that all the runtime needs are complied or are satisfied in order to kind of unlock all the composable features at runtime. So the compiler plugin will take all the composable functions and will append this implicit parameter that is going to be the composer for all the on all the call sides to all the composable functions, and the composer is actually the object that will drive the whole runtime of Jetpack Compose because it's going to drive the composition, recomposition, and all that. So we want it to be present at all levels, you know. Here's an example of a composable that I grabbed from some tag from Leland from the Kotlin Conf 2019, I think it was, what it was showing this kind of counter composable that shows how the compiler introduces or passes this extra parameter that is going to be the composer across all the composable calls, like this one, the remember one that is also a composable function, so it forwards the composer to it, also the button, the text, and all that. And some also compile time generated unique keys that are used to refer to those elements when they are stored in this representation, in-memory representation of the UI that we are going to create using the runtime, and that we will dive into in a second also. That's going to be the slot table. But they need to have these keys to refer to those elements, so you can then later on, or the runtime is able to later on find those elements or look for those elements and then retrieve them and compare for things like, for example, smart recomposition, to skip recomposition or things like that. But how do we ensure, or how does Jetpack Compose ensure that the composer is available across all the composable levels? Well, in that sense, it uses compile time checks in the front-end phase of the compiler. If you're aware with how compiler and compiler plugins are usually written, you usually have like two phases, the front end and the back end, and the front end is usually meant for different things, but among those, for example, performing a lot of checks, very fast checks, like for example that you are calling your composable functions from the correct environments or from the correct places or things like that. So you get static analysis on that phase, right, overall. So you can get like red underline or warnings or things like that depending on how you're using the library. And one of those checks that the library or the compiler plugin provides is that composable functions can only be called from other composable functions, right? So in that sense, we are imposing, or the library is imposing, a calling context that is going to be a requirement that needs to be there. Otherwise, you cannot really call these UI effects, we could say, that the composable functions are from anywhere, right? You need to be from a safe environment that is prepared to run these effects of this nature, we could say. So in that sense, they create this calling context requirement, and that's going to end up enforcing the requirement for the whole composable call stack altogether. This is good because that's the way that the compiler has to know that it's going to be all composable functions, so it can just go ahead, replace them by the new version of them, including the required metadata and composer, passing the composer around and everything, and there you go, the composer is available at all levels on your composition or on your composable tree. So once we have everything generated at compile time, and once we have the runtime ready to go, we can start with it. And the runtime in Compose is somehow like, it's interesting because it applies this idea of declarative programming or concern separation. So it creates this in-memory description of the program that describes how your UI is going to look in memory. But it's more like deferred effects. It's like effects or gradual changes that can be used or can be interpreted later on to yield or materialize a final snapshot version of the UI that you can display on a screen or whatever. So in that sense, you have like an in-memory representation of the program, or in this case, if you are using Compose for UI, an in-memory representation of how your UI is going to look whenever you materialize it. But it needs an interpreter afterwards, an interpreter that will read all that in-memory structure, and then from it and from how it looks, it will be able to derive or materialize a UI for a snapshot in time, we could say. So that's cool because the interpreter is decoupled from the actual program. You have the program that is totally agnostic of how it's going to be interpreted. And in that sense, you can, for example, leverage things like runtime optimizations or things like that, because the runtime is able to see the whole picture of how the composable tree is going to look, and then it can decide how to, for example, optimize the materialization of it. Like, for example, if it needs to recompose or something like that, it could then decide to offload different compositions to different threads or things like that. That could be, or even skip some redundant recompositions or things like that. But that's only possible because the whole program is there, the big picture in memory, right? So this in-memory representation of our UI is going to be the slot table in Compose. So the composer is taking care of adding elements to the slot table the first time it reads the composable call stack, because the slot table starts completely empty, right? And then the composer starts reading a composable call stack, and then it starts adding elements to the table. And then for every recomposition, those elements or that metadata, we could say, that we are storing in the slot table needs to stay up to date, right? Because you could have like conditional logics or something in your UI, and then your structure might have changed. And in that sense, that needs to be communicated to the slot table via the composer. So it stays up to date all the way, or at every point in time. The table is later on going to be interpreted to materialize final UI from it, or to yield the final result of the composable structure in that sense. And that's going to be the UI module that we will use for that, and we will explain step by step how it works in that sense. But does it need to be UI? Because we've been talking about UI all this time, but that's not really necessary, right? Compose and the Compose runtime works with generic node types, meaning that of type N, right? So it's like a generic type, meaning that all the logics for composition, recomposition, storing changes on the table and everything is written targeting this n generic parameter or type parameter. And in that sense, you can really pick the layout node type you want to use, right? So Compose is open to optimize large call graphs or trees composed of generic nodes. And it's the applier or this interpreter that we will dive into in a second, the one that will pick an actual type for the nodes and will provide an implementation of this applier interface for interpreting the whole in-memory tree. So in that sense, you can really use Compose for optimized call graphs for different problems, not only UI, and we will try to give some examples on this also. Right, so when you create a layout or when you create you call a composable function, that doesn't really store like a final UI element on the table or anything like that. What it does is like emitting a change to the slot table. So it's more like a description of an effect that is waiting for this, waiting to be interpreted. You can see that here, like for example, this is how the layout works or how it's implemented under the hood. So if you're using any layouts from the material component, sorry, the material design, the material compose material library, or from the foundation library like Box or whatever. At the end of the day, all those are written as layouts under the hood. And layout is not really creating a UI element, but it's emitting a change to add an element or to add a node to the table. So what you get on the inside is a call to this emit function that states the type of the node we are going to be using, which is layout node, which is just how Compose UI represents the different UI elements in memory. And then you say what type of node you are going to be using for the applier. And what you do is providing a constructor that will be executed whenever this change is materialized, but not before, to finally create the layout node and attach it. But before that, it's just like a description, right, on how to create it. A function for initializing it, which is the update function. Like you can see here, it's initializing the measure blocks with a helper, the density ambient, the layout direction, a few things using some helpers. So this is a lambda where those things can live to kind of initialize the whole thing after creating it. Also a couple more parameters and then the children. But the important thing here is that you are emitting a change over the table, right? And that ultimately records an operation over the applier for inserting the element. So as you can see, this is just a recorded effect, a recorded operation that will end up yielding UI or materializing UI, but at the time of the UI pass, we could say, whenever the applier runs and materializes the whole in-memory structure to yield a valid snapshot of the UI in time. So these changes are basically type values over lambdas. So it's a lambda that represents an effect. Every change is a lambda that takes 3 arguments and returns unit, meaning that it's an actual effect. It's going to perform an effect. So it takes the applier, basically because that's going to be how we materialize the change when the time comes. It gets a reference to the slot writer to be able to write into the slot table. And it gets a reference to the lifecycle manager. And that's important because when we are adding or removing elements, for example, from the table, you might want to trigger those lifecycle events like on enter or on leave, because if you are adding a new element, you want to make sure that after adding it, you are calling the actual on enter callback. So all the observers for the lifecycle get that event communicated, right? And the same when you remove an element, you want to call on leave. So in that sense, there needs to be a reference accessible for the lifecycle manager, so you can do that. But the lifecycle manager also keeps track of side effects, which is important, right? A side effect is actually another type of change you can be recording with Jetpack Compose. Because we not only record effects or changes for adding and removing or moving elements around or replacing elements, but we also record things like side effects, also any composable function calls and much more. So some examples that we can, the things we can find stored in the slot table or recorded as changes can be operations to add or remove or replace UI nodes, operations to store state, operations to store remembered data, composable function calls and all their parameters also, providers and ambients, because those are also composable functions, and even side effects of the composition lifecycle, right? The ones that observe events like on enter or leave. So yeah, there are many different types of nodes we can find in the slot table. If you want to know a little or to learn a little bit more about how the slot table works on the inside and the internals, I think the talk I mentioned before by Leland Richardson, I think it's a very good one. And even if it's from 2019, I think it's still remains pretty valid today. So yeah, I definitely recommend it. Okay, so we are in the compose runtime. We have this idea of how to create the slot table or how it's updated whenever we are processing all the composable call stack, how it gets built in memory and it needs to be interpreted later on. But let's try to give a little bit of order to all these things. The first thing that it happens when you process a composable tree from the runtime is the composition itself. So the composition will read your composable tree, and it will basically start filling up all that slot table with relevant information about the composition, right? That's going to be information that later on can be interpreted by the applier to finally yield some UI from it or materialize some UI from it. I keep saying UI, but remember that we could be using any use case, not even to represent UI. We could be using this to represent any other node trees with other node types. So in that sense, the applier will still need to interpret that in-memory structure to yield a final result or materialize a final result from all that structure, right? I'm just going to keep saying UI because it simplifies a lot the example, and I think it's probably a good use case to use to drive the presentation. So yeah, whenever the composition completes, the applier applies all those recorded changes. And at that point, that's where the UI is materialized, and you start seeing the UI on a screen. So your composable is already visible. It's not only some representation in memory as it was until now. So it's already on the screen, and then the time for lifecycle events comes. And at that point, all the lifecycle events that have been recording up to this moment are triggered in order. The leave on leave events happen first, then all the on enter ones, and then afterwards, and only after that, all lifecycle events, we have the side effects. All the recorded side effects will run at that point. The order is intentionally deterministic here, so it's always it's impossible to run, for example, a side effect before on enter. So on enter always happens before. And then whenever that has happened, you cannot start running side effects afterwards. So there is no this scenario where you try to run a side effect too fast or too early in the composable life cycle, right? The same thing happens the other way around. If there is an on-leave event taking place, and then because composable leaves the composition, and then you couldn't really call a side effect on it. So because at that moment, all the side effects recorded for the composable call get removed. So they are not recorded anymore. And in that sense, it's not possible to try to run a side effect either after the composable left the screen, okay? So, but what about the recomposition? How does it work? Because we didn't say a word about this yet. Okay, so the composer can discard pending compositions when the composition fails, because that's always possible. But it can also smartly skip recomposition when required. And to do that, for this smart recomposition and escape recompositions when it's possible or when possible, there is this recomposer scope. So if you peek into how it looks whenever the compiler takes place, it runs and it adds all the boilerplate to the actual composable, what it does is inserting this start and end calls, wrapping your composable logics, and then the composer end call returns a nullable value, and then there is this update scope added right afterwards. It's really interesting here that they are using this nullable, because with this nullable they indicate that the recomposition is not needed when it's null. So in that sense, this code is going to return null whenever your composable is not reading any observable model or any observable state, we could say. And in that case, there is no reason to train the runtime to learn how to recompose this composable, right? Because there is not going to be need for recomposing it at all, okay? In the other hand, if your composable is reading, for example, a recorded state or something like that, if it's reading from a state snapshot, it will return something that's non-null, and it will just be able to teach the runtime how to recompose this composable, okay? So that recompose scope is basically what will get called by the recomposer whenever it tries to, whenever the time comes for triggering a recomposition for this element. Another thing that the runtime takes care of is the positional memorization, which is this ability to remember the result of a composable call, so you avoid computing it again. For example, the result of the remember function, if you're familiar with it, so you can use that. And that's part of the runtime also, because that's a result that is stored in the slot table, and then the next time you try to access it by index, if you remember those indexes that we were generating at compile time, at that moment the runtime can say, okay, I'm going to compare this copy or this snapshot of the state with the one I already calculated, or I'm going to compare the keys for the elements, and if I know that the state hasn't really varied, I can just return it as is without computing it again, okay? And it just reads it from the slot table and returns it. So you can see some examples of these here. You have some colors for calculating a vertical gradient scheme. So you are using the remembering functions to, for example, computing the colors you want to use for the gradient, creating some mutable state, and maybe calculating the actual gradient. You remember all that, so you make sure that you can use it right away. And after every further recomposition, you know that the values are going to be used as they are without the need for calculating all that again. Okay, so you're saving a lot of computational time thanks to this function and this positional memorization ability. One thing to remember here is that the runtime is very coupled to Kotlin-esque routines, because we've been talking a lot about how the composition ends up creating all this in-memory structure, but we didn't say a word about how that actually takes place. And well, it happens by the power of Kotlin-esque routines and structure concurrency, because as we said, there is this chance of having in the future, for example, parallel recomposition or offloading recompositions to different threads or reordering composition. So there's going to be a lot of need for coordination there. So the power of structure concurrency is a pillar, we could say, in how the composer and the recomposer work. For example, also for automatic cancellation, because we are going to have the effect handlers that perform automatic cancellation when the composable leaves the screen or leaves the composition, and in that sense, that's going to be achieved also by using the benefits of a structured concurrency automatically for you. So you can't really replace it. It's not open, so you replace this kind of runtime library of Kotlin-esque routines. But you have this applier that is an interface. It's an abstraction working over the generic node types, that you can basically implement and provide your own implementation for. So in that sense, you can interpret that in-memory structure the way you want, and for example, give support for different libraries, like some examples we'll see in a second. So, well, we have the compiler, we have the runtime, we kind of have a big idea of how both work together, but what about the UI? So the UI is basically that ultimate moment when we finally want to materialize UI from our structure in memory. So it's kind of bridging this gap between the runtime and the platform. It's going to be the applier, the one in charge of doing this. So the applier that works over an n generic type for applying all those changes of n, of type n, it's going to be the one materializing the whole thing in the end. It provides integration with the device in terms of layout drawing, using Skia, user input, and all that. So This is more or less like the same diagram again. So we have the in-memory description of the program, then the interpreter that interprets it, and then you yield a final snapshot, we could say, of the UI state or the UI on your device. So there is a built-in applier implementation for Android in Compose UI, that is the UI applier, which is basically supporting both concepts of view groups and composable layout nodes. So it's a hybrid solution that for now it's basically able to materialize a final UI out of your composable tree metadata that is on the slot table. And it supports both ideas. So here's a sneak peek of how it works. It keeps a stack of any, which is the node type in this case, because that's like the common pattern for both view groups and composable layout nodes. It keeps a reference to the current node, because this is like a visitor. It goes over the whole node tree one by one, visiting it and materializing it when required. So it keeps track of the current node that is visiting, and then it has functions for adding new nodes to the actual stack and consuming them. So this app function is the one that peeks in the stack, pops an element from the stack, and then it goes like, okay, I take the parent, and if my parent is a view group and the instance I want to materialize is a view, it's all about attaching it, right? This is how we are finally attaching the views, so they are visible on UI using the view system add view call. But if I'm a layout node and my parent is a view group, I need to wrap myself into an Android Compose view, right? Because that's how you can integrate composable layout nodes into view groups. But if my parent is a layout node, so it's a composable, and I am a view, there is another parent that is the view block holder, another structure that can be used to insert views into composables. So it's like the other way around. But if my parent is a layout node or I'm a layout node, I can just use the layout node APIs to insert myself into the parent. So overall, it's able to resolve how we finally attach this element to the actual UI, and that's how we materialized this in-memory representation of the layout, that is the layout node, into a final, an ultimate visible UI snapshot or UI version. So layout node works as an in-memory representation of a UI node. It's attached, it has a reference to its parent, and then the parent has a reference to its parent, and whenever you are on the root of the call stack, you have a reference to the owner, and the owner is like the ultimate connection or underlying connection with the view system. And the layout node keeps all this information about the layout regarding how it needs to measure itself, its children. It keeps a list of its children. It keeps also track of all these APIs for right to left rendering, the set index for positioning the elements by depth and all that kind of stuff. So a lot of different ideas that are covered here that are basically what the layout is covering, but overall it's all about keeping track of all the children, how the children are measured, and how the children are placed on a screen, among other things. So yeah, there are other use cases that we could show on how to interpret changes on this slot table by providing different custom implementations of the applier and custom node types. Like, for example, UI testing libraries that could interpret changes on the table by creating abstractions you can assert over instead of rendering actual UI, right? But also for supporting other platforms like desktop or web, you can imagine node types like DOM elements or things like that. And an applier that instead of attaching stuff to the Android view system, it ends up, I don't know, using whatever the web uses for rendering a virtual DOM. So, but other examples like controlling hardware to minimize, for example, commands to reflect a change. I don't know. Different ideas, different use cases, but it all depends on how imaginative you can be on this. Okay, there are not many examples out there, but there is a really good article that I read lately about how to create a web app using Compose with some server-side composition and client communication with a client via WebSockets and so on. And that one provides a very good example of how to create a custom applier and pick a custom type for the nodes. And I think it's worth it because there are not many posts about this out there yet, and this one is very, very didactic. It was written by Andrei Shikov, by the way. And finally, let's go over effect handlers. Effect handlers are actually part of the runtime. I just skipped those because they probably take a little bit more time, and I wanted to address them separately. But think of them like this. Any apps contain side effects, right? But you don't really want to run your effects right inside your composables because your composables might recompose many times, and that's going to cause your effects to run every single time, and that could cause a lot of problems or race conditions. So in that sense, you want to wrap them into an effect handler, and the effect handler you pick will take care of things like, for example, that the effect runs on the correct life cycle step and not before that moment, or in the correct environment, like for example in a convenient dispatcher, like the main one or any other one. And also that these effects are bound to the composable lifecycle. Like you make sure that whenever it enters the composition, it runs, and it gets cancelled, for example, when it leaves the composition or things like that. So in that sense, they are going to be giving you this kind of safety network that you can run your effects on safely. I want to just share a disclaimer here because the effect handlers are varying so frequently lately because they are under heavy development iterations at this point. So these are the names, and the handlers available, as of today in the latest snapshot version of Compose, which is there is the Alpha 07, and this is like probably the most up-to-date version of it, the snapshot, which kind of has all the development branch ongoing. So you can expect changes, right? So in the world of effect handlers, we have two big categories, the suspending and the non-suspending effects. So the non-suspending ones are the ones that you would use, for example, for initializing a callback whenever your composable enters composition and dispose it in the end, release it in the end to avoid leaks or things like that. So nothing related to suspend effects, and suspending effects are for that, right? So if you want to load some data from the network for feeding a state, for rendering the initial state of a screen or something like that, or anything that involves a suspended effect, not only related to loading data, you will use any of these suspending effect handlers for. So disposable effect, and for the people that has been using on commit and on dispose, it's just like the same idea. And it's basically this idea of a side effect of the composition lifecycle. So it's observing on enter and on leave. So it will run on enter as soon as your composable enters the composition the first time. And then it will dispose in the end whenever it leaves the composition. But it's also going to run every time these subjects change. So you can pass a subject to it for saying like, okay, if there is a recomposition and then I see that this subject has changed since last time, I will rerun the effect one more time. And for rerunning the effect, it will dispose it first if it was already running, and then run the effect again, right? So it's going to run the first time, and then on every recomposition, only if this subject has changed. Okay, and it enforces us to return an on dispose block in the end, so we kind of dispose whatever we are acquiring with this effect in the beginning on enter. So we dispose it on leave. We make sure that everything stays out of any possible leaks or anything like that. Right, so in this case we have a back press handler. We get a dispatcher for handling back press events, a callback, and then let's say that whenever the dispatcher changes, we want to make sure that we attach the callback and then we dispose it in the end, right? If you call disposal effect with a non-variable or a constant subject like unit or true or anything like that, that's basically meaning that it will run just the first time. So it's equivalent to this old onActive or onCommit unit or onCommit true, which was equivalent. So it's basically this idea of an effect that runs only when entering composition and never more, okay? Still, it will require you to dispose in the end. There is the requirement for returning a dispose callback in the end for releasing whatever you acquired. There is side effect of also, which is more like a fire on this composition or forget, we could say, because if composition fails, it gets discarded. But this one is for example, publishing updates to objects outside of the scope of this composable function. Like for example, here we have, and actually it runs on every composition and recomposition. Like for example, here we have this touch handler, which is using a drawer, a navigation drawer. So we remember some drawer state as closed, for example, by default. And we go like, okay, every time you enter the composition or any recomposition, you're going to check if it's open, and in that case, you will update or toggle this drawer touch handler, for example, for enabling touch or not, touch events or disabling them. So in that sense, you are like publishing updates to an object that is totally, or a state that is outside of the scope of your composable function, that is not driven by any compose state snapshot or anything like that. So a pure side effect, we could say, for posting or keeping that up to date on every composition and recomposition. There is invalidate also, which is invalidate is like its counterpart for the view system. So in this case, what it does is whenever you call it, it enforces its invalidating the composition locally. So that's going to enforce a recomposition for your composable. So it's like manually enforcing recomposition, right? It's important to notice here that this one should be used sparingly, because you always want to go for observing a state instead and leveraging a smart recomposition, right? So whenever the state varies, there's going to be an automatic recomposition triggered for you, so you don't need to do it manually. So in that sense, you can use the power of compose and smart recomposition to do that, and then you are good to go. And for animations, for example, if you were used to represent complex animations using, these frame-based animations using the canvas, where you manually invalidated on every rendering tick or something like that, that's not needed either in Compose, because there are APIs for waiting for the next rendering frame. And you can do the same with those. So in that sense, this is not going to be handy or not convenient. But for example, it can work when you have a source of truth that is not a composed state, right? If you are loading your data in, for example, this presenter, let's say the presenter is not feeding a UI state or anything like that, not a composable state snapshot, but a simple variable. So in that sense, whenever you load it, you might want to enforce recomposition manually. But this is a very, very edgy use case, I would say, and I don't think you are going to end up using invalidate a lot. Just wanted to share it because it's there, and yeah, who knows. About suspended effects, just a couple of them, and I think we'll be done. There is remember coroutine scope to run your suspended effects, so it's going to return a coroutine scope bounded by this composition lifecycle or this composable lifecycle. So that means that, it will live across compositions, so it will return every time the same scope on every recomposition. But whenever the composable leaves the composition, the scope gets cancelled. So any jobs or any child jobs that you have been submitting to it or creating from it will automatically get cancelled. So that's very interesting for suspended effects that run, for example, as a result of, or as a response of user interactions, right? Like for example, if you have, let's say, a text input, and every time the text changes, you want to do this kind of throttling we were used to do before on UI sometimes. Or you cancel the previous job reference, and then you run a new one over the same scope with a delay for some threshold, and then you perform a request for searching the query with the query text on the network or whatever, and then you feed the state as a result. So in that sense, the important point here is that every time we create a new job, we are using the same scope that we have obtained with the remember coroutine scope. So whenever the composable is finally going to leave the screen, it will cancel the scope and cancel all the potential ongoing jobs there, right? So you are making sure that you don't leak anything. In the same way, there is launched effect. Launched effect is basically for these suspended effects for loading, like the initial data to show on a screen. For example, you want to render a feed of items and you need to load it from network or wherever first, and that is a suspended operation. You can use launched effect for that. So this and the previous one run on the applier dispatcher, which is where all the changes in the slot table are finally materialized, which uses to be the Android UI dispatcher.main, which is very similar to the dispatcher's main from Kotlin and coroutines, but this one is getting or retaining a reference to the current choreographer and also a main looper. So it's able to kind of trigger the effect whenever the choreographer, the next rendering take arrives, or when the main looper is able to loop, like whatever happens first, but very similar, right? So in that sense, those are gonna run in that one by default. And again, you get the effect canceled in the end if when leaving the composition, right? The important point here is that it also has these convenient parameters that can be one or many, actually. I'm not sure if I said that, for the subjects. So the effect is going to run again every time that varies after recompositions, right? So every time it needs to relaunch it, it will cancel it first and then relaunch it, okay? And also gets cancelled when leaving the composition. So this one is useful to span a job that outlives the composition and lives across different recompositions. And then finally, there is this produce state, which is this just like syntax sugar over launched effect. For launched effects that end up feeding a snapshot of a state snapshot in Compose, you can use produce state, which is just like an overload of it, we could say, like a syntax sugar, because it actually relies on launched effect. So this one provides this option for providing an initial default value for the state. Also one or many subjects, so it runs again if those vary, and then you put the effect on the inside. So for things like suspended effects that depends on an input that might vary, like for example this event ID in this case, so you relaunch it every time that varies also, it might be an interesting pick. And other than that, I had something for configuration changes, but it would have been a really long talk, so this is going to be all for now. I will probably write a post or something. I also wanted to say thank you to Adam Powell because he helped a lot on digging into the Composer, the Jetpack Composer internals overall, and clarifying a lot of things on the effect handlers these days. So thank you for that. And thanks everyone for attending. So time for questions if you got any, and if we got time. Thank you very much.